Okay, this is a physicist explaining everything you need to know about differential equations in one slide. The idea of differential equations is that what is known is a relationship between a function, f, we're probably going to call this x, but this could be f of t or f of x, and its derivatives. So you don't know what the function is, but you know how the derivatives of the function relate to the function itself. So that's kind of the starting point for differential equations, at least from a physics point of view. So then there's a few strategies of how you deal with this. And again, within differential equations, there's also a lot of theory that goes into this. But as a physicist, I just want to solve this equation. It's a tool for me. And there's a few strategies here. And this might be a little surprising if you've mostly dealt with calculus. So the first strategy, and this is the one that is really the most powerful, is that you recognize the differential equation and you write down the answer. Now, I want to point this out because this is really the opposite of how I demand that you do physics in the class. I always say you have to show your work, even if you recognize that, okay, it's a flat surface, normal force equals mg. I say show why that's true. Well, in differential equations, you frequently recognize the answer and you say, okay, this is the answer. Well, you can then prove it by guessing and checking. So when you have a differential equation, it really helps if you recognize it and you say, I know what the answer is to this. And then you can prove it by guessing and checking. There's an idea, a theorem in differential equations that effectively, once you know the solution, that is the only solution. It has to be general enough, and frequently, as you go to higher order differential equations, there's actually more parts to the solution. But once you know one solution, you actually know that it is the solution. So that's why guessing and checking is completely valid. Now, another approach, and this is why differential equations can take a whole class, is that certain forms of differential equations have recipes on how you solve them. So you might not look at it and know exactly what the answer is, but you know how to rearrange it or test something to define the answer. So this really still, in my mind, goes with recognizing it, and frequently you're guessing and checking something, and that is the recipe. Now, if you want to get even fancier, you frequently need to transform your differential equation or manipulate it a little bit to get it back into either a form you recognize and know exactly what the answer is or something you have a recipe for. And you do this in calculus a lot when you do transformation of variables. So it's a little more complicated, but the same idea, where you use mathematical rules to get it into a form where you now recognize it. Let's say none of that works. If you were to hand me, someone with a PhD in physics who has taken lots of math related to this, a differential equation, and I didn't just look at it and know either what the recipe is or what the answer is, I would open up a textbook and start looking for something that it looks like. If that didn't work, I would consult other people, i.e., someone who teaches differential equations. And if that person looked at it and said that she didn't know how to solve it either, because again, she's basically using this list up here, I would then solve it computationally. So this is the point about differential equations. Effectively, you're either recognizing it, following a recipe, which requires recognizing it in a way, or doing the transformation and then following those. So with that, let's actually practice a little bit this recognizing and guessing and checking. So if I have some function, which is a function in this case of x, I don't know what it is, and the function is equal to its own derivative, I now have to write down what f is. And again, once I guess one form of this that's general enough, I know that that's the only answer. So even if you haven't finished Calc 2, even if you haven't taken differential equations, you can do this. Because effectively, I am posing the question to you, what is a function that when you take the derivative, you get the same function back? Well, pause the video, think about it briefly. But in this case, that would be f of x equals e to the x. You know that e to the x, the derivative of it, is e to the x. The caveat being we should put a constant out in front, because e to the x, when you take the derivative, if there's an a in front, that a just stays there. So if we guessed and checked, we would say, yeah, a e to the x. Well, when I take the derivative, I get a e to the x. I guessed and checked and that worked. Okay, not too hard. So let's do a slightly harder one. Now, my function is a function of t. No big deal. Same thing. Now, the function is equal to its negative derivative. Okay. Well, let's be crazy. Let's try something like maybe f of t equals t. Let's try that. Well, df dt equals 1. And keep in mind that you can't say, oh, t equals 1. No, this has to be true for all values of x or all values of t. So clearly, that does not work. That was a bad guess, but that's okay. You guessed, you checked, it didn't work. Well, notice that this differential equation is really similar to this differential equation, except x became t, that doesn't actually matter, and a minus sign appeared. Well, what if now f of t equals a e to the negative t, right? So now I have my function is a e to the negative t, and then when I take the derivative of that, I'm just using this minus sign here. So that's what that is. So now I'm going to take the derivative. The derivative of a e to the negative t, that negative comes down, right? The negative comes down out front. And so I then have negative a e to the negative t. Well, a negative times a negative becomes positives, and hey, look, that's equal. So I found my function here. And again, similar answers, similar differential equations. Now, instead of calling it f, I'm calling my function x. No big deal. Now my function x is a function of t. But now I have the second derivative. Now there's a subtlety here in that my answer actually has to have two terms, or you can think of it as finding two answers and then adding them together in a general way. But we now have a second derivative and a minus sign. So if there wasn't a minus sign, and I said what function is equal to its second derivative, well, the answer is, hey, a e to the x. But now we have a minus sign. And it's not true that a e to the x, its second derivative, doesn't get a minus sign. But you actually know two functions that do. You know that the second derivative with respect to time of cosine of t equals negative cosine of t. However, one thing to be careful of is that the second derivative of sine of t is also equal to negative sine of t. So we have two solutions here, and one of the ways that we could generalize it is by adding it together. We could also actually just call this cosine of t plus phi, right? That's another way to make this more general. So, we've been talking about cosine. I have an equation now that gives me a cosine. So the answer to this differential equation, and you can really take the second derivative of this to check, is a, where again a is some unknown amplitude that would just stay there, cosine of t plus phi naught, which is adjusting for the fact that both cosine and sine are solutions to this. So the mathematical idea is because it's a second order differential equation, you have a second derivative, you have two constants. Just like integrating twice, you get two constants. And in this case, one is the a, one is the phi naught. So then, what about now? What if instead of up here, we never had coefficients out in front other than this minus sign? Now I have a minus sign and a coefficient. So I take the second derivative, and that's equal to minus a times my original function. Now I have to be careful because previously I've been using a to just be some unknown coefficient, but now it's actually something specific. It's in my original equation. And note that before I had been putting my minus signs with my derivatives, now I've moved it over here. That's fine. What this is actually going to work out to be, and again, the best way to check is to flat out take the second derivative and verify that it's true, is that, and I'm not going to use a anymore for the sake of things getting confusing. I'm going to call this, what's a nice I'm going to call this alpha. Not alpha meaning angular acceleration, but just a variable. So I still have alpha. And again, notice that I could cancel this minus sign by multiplying both things by minus. So this minus part is really similar. So it's just, what do I do with this a? Well, so I have alpha cosine. Well, keep in mind that if I had something multiplied by t, it would be multiplied out front when I took the derivative. But then when I take the second derivative, that happens again. So this here is square root of a t plus phi naught. Because again, I take my first derivative, cosine becomes minus sine, but I use the chain rule, so a square root of a comes out. I then take the derivative of again, and another square root of a comes out. So this is my new solution, where I have some coefficient out front, which is not what was in the problem originally, but this value that was in the problem becomes multiplied by my t. And again, you have this phi naught accounting for the fact that it's a second order. So this is the idea of differential equations. Again, I haven't taught you the entire class, but everything that you need to know for Physics 202 is going to be in this form here. So after this, we'll go back to talking about the physics part of it. If you haven't had differential equations though, the book also goes through this. And again, to really show that this is true, just take its second derivative and show that this equation is true.